start again. Okay, so resume with Davi Lima from Universidade Federal de Alagoas, talking about counting and Hausdorff measures for integers and P-adic integers. Davi?
So, thank you, Felipe. I would like to thank the organizers for the invitation and congratulate for this very nice workshop. Well, this is a joint work with my friend Alex Espinosa. He is there included. So I'm going to talk about for some fractal geometric aspects of the subsets of the integers numbers. So what is this important? So how can we measure a set of integers numbers? From combinatorics, analytic number theory, and ergodic theory, we commonly use density, the notion of density. For us, we use the Maynard density. The Maynard density of a set E is the lim sup of the number of the elements of E in an interval of integers divided by the number of the elements of the integers, and then we take the lim sup on the class of the intervals on the integers. For example, we have the Maynard density of arithmetic progression. And if we take the prime numbers followed by the prime number theory, then the Maynard density is equal to 0. We can imagine the Maynard density as a natural parallel with the Lebesgue measure. But the density is not a measure. Szemerédi in 1975 showed that if you take a subset of integers with positive density, then this set has arithmetic progressions with arbitrarily large length. Rindman shows that if you take a set with positive density, then we translate, and we obtain a set, a big set, almost full density. Then it's natural to ask what about dense sets with Maynard density 0? Green and Tao show for the set of the prime numbers that if you take this set, then also has arithmetic progressions with arbitrary length. So it's important to ask if we have a fractal geometry in the sets of the integers numbers. Yuri Lima and Gugu defined these guys, the S counting measure, equals to the lim sup of the number of the elements of the set E intersection I divided by the number of the elements of I to the power S. And this S here, when S is equal to 1, then we have, in fact, the Maynard density, okay? And what about this guy? It's not difficult to see that there is a parameter S0 such that before the S0 we have the S counting measure infinity, and after this parameter we have the S counting measure is equal to 0. This parameter is called counting dimension of the set E. And we have, in fact, a formula. This is the formula where we take the logarithm here and logarithm here. Okay. For example, we have the counting dimension of the prime numbers is equal to 1. Then the prime numbers in the sense of the density is a small set, but in the sense of the dimension, this dimension, is a large set. If we take a set or a subset of integers and lambda are a real number, we define the floor of the lambda e in this way. Google and Yuri showed a Marstrand-type theorem for E and F nice sets. We have this dimension formula, the counting dimension of E plus floor lambda F equals to the minimum of 1 and the sum of the counting dimensions. Moreover, if the sum of the dimensions is greater than 1, then for Lebesgue almost every point lambda, we have this guy here with positive density. This is a first result in this the direction that a fractal geometry implies in combinatorial information of the sum set. We have this parallel, the Banach density with the Lebesgue measure, and the counting dimension with the Hausdorff dimension. We will explain the Hausdorff dimension after. In this year, Daniel Glasscock, Joel Moreira, and Florian Richter explored the fractal structure that exists in R and propose a way to study fractal geometry of 4 subsets of Z. And if you want, this is the paper, Additive and Geometric Transversality of Fractal Sets in the Integers. So, and our approach is looking for P-adic numbers. Integers are like these popcorn kernels, so well-behaved and respecting each other's space. But I am dynamicist, then I like to kill. So we take your prime number, your favorite prime number, and we define the P-adic valuation as the greatest power with p to the power k divided n. This is the P-adic valuation. These some examples here. We can extend this P-adic valuation to rational numbers in this way. And given this P-adic valuation, we define an absolute value on Q in this way. The absolute value of a rational number is p to the minus its P-adic valuation. And you can define a metric. The completion of the rational numbers with this metric is called P-adic numbers. For example, if we take this sequence, then we have this formula. You can show for your brother of 15 years old. Not that if you take an integer number, then the absolute value is bounded by 1. That is, the integer numbers is a subset of this ball. And this ball is called the P-adic integers. So the P-adic integers is the unit ball of the P-adic numbers. Some facts of the integers, P-adic integers. ZP is a compact topological group. Every point can be associated to a sequence in 0, 1 to p minus 1. And there is a half measure, mu p, such that this guy has this measure. In symbolic dynamics, here, this is a cylinder, this ball is a cylinder, and this P-adic measure is a Bernoulli measure. Alex and I proved this instance of Furstenberg correspondence principle, which says that if we take a closed set in ZP, then its projection on Z is bounded by the P-adic measure. And if we have the boundary of the set F with measure 0, then we have it, then the equality holds. We have some proofs of the theorem, but the combinatorial proof allows to conclude some nice properties which we explain later. So, consequence of this theorem A. If we take the two subsets of Z, of the integers numbers, then the difference, the arithmetic difference between these two sets is the set of the difference. Then this corollary is a combinatorial simple fact, but this illustrates our result. Then if you take two sets such that the sum of the Banach density is greater than 1, then for every prime p and every k natural number, we have that the arithmetic difference contains multiples of p to the power k. Note that this hypothesis implies that for every prime p, we have that this measure here is greater than 1 because the hypothesis and our theorem. But this implies that the intersection of its two closure is positive. Then we can take a point in this intersection and this condition implies that there exists for every k, we can take m in E and n in F such that x minus m is smaller than 2 to the power minus k, and x minus n is smaller than p to the power minus k. But two inequalities implies that m minus n is smaller than p to the power minus k. That is, m is equivalent to n modulo p to the power k. Then this is a simple consequence of our theorem A, and this shows that if we understand, this is the Banach density. If you understand the relation between the S counting measure and the S Hausdorff measure, we can obtain another fact, combinatorial facts on the sets. Here is the proof. This is the proof. So what can we say for zero density sets? Before we were thinking that the Banach density is parallel with the Lebesgue measure. But now we can think that the Banach density is parallel with the P-adic measure. then maybe it is possible that the S counting measure can be related to the S Hausdorff measure. So remember, the S Hausdorff measure is we take a cover of our set and look for this type of sums where the diameter of the balls is smaller than delta. And we take the limit where delta goes to 0. This is the Hausdorff measure. And the Hausdorff dimension is the infimum of these guys here, such that the Hausdorff measure is 0. So our strategies is the following. We look for what is this guy here. We have a closed set in ZP, and we intersect with a ball. But this is a local way to see this set in ZP. And we try to recover properties for this guy in the integers numbers. Then we intersect with an interval I. And we count the number of the elements of this. And divide by the number of the elements in a ball intersection this interval I and to the power S. This guy here is an arithmetical progression of common difference p to the power n. And we look for the lim sup. But this ball needs to decrease. Then we take the lim sup of n, in n, here. This guy looks like a density, and in fact, we have this. Eta S is a density with respect to the S counting measure. Using these local notions, we can prove the following theorem. If we take a closed set of the P-adic integers with S Hausdorff dimension, S Hausdorff measure finite, and this lim sup is bounded by a constant, then the S counting measure is bounded by the integral of this density with respect to the S Hausdorff measure. In this way, we can relate it to S counting measure with S Hausdorff measure. So every result here is for a closed set, and we intersect it with the integers numbers. Our strategy is the following. We take a subset of the integers numbers, and we look for its P-adic closure. After we intersect this with the integers numbers. But this guy increase with respect to this. Then it's natural to ask for search for sets E such that these occur. If you want to apply our results. So theorem B implies theorem A because when S is equal to 1, then this expression here is for s equals to 1, this is smaller than 1. And the one-dimensional Hausdorff measure is, in fact, the p-adic the Hall measure of the group ZP. Then we have the H1 is the density. Here is the Maynard density. He is bounded by 1, and he is the p-adic measure. Then the Maynard density is smaller than the p-adic measure. So here we explain this strategy. We call the pi p of f the p-adic projection of the set E. So we try to understand the subsets of the integer numbers, which is a projection of a closed set in ZP. In fact, this is equivalent to this set. If we prove that if you have a set which satisfies this condition, then in fact we can take F its closure. And the other thing is a topological aspect of the p-adic numbers. It's clear that the p-adic closure is equal to our set union this guy here, the accumulation points which does not belong to E. And we have a set E which is the projection of its closure if and only if this intersection is empty. Then we try to give combinatorial conditions on a set E such that we have this. Some examples of the p-adic embedding, closure embedding, and the p-adic projection. The set here is the prime number grows a lot because the closure of the p-adic number is a union of p minus 1 balls and a point P. And the projection of a ball is an arithmetic progression with common difference p to the power n. If we denote, we take p greater than 3 here, and we denote the class of the subsets of the integer numbers such that 0 and p minus 1 does not appear in the p-adic expansion of these numbers. So the collections. So in this class, we have that E is its projection. E is the projection of its closure. So, but all the sets in this class has Maynard density 0 because its closure it's not difficult to show that this guy has density equals to 0. Then in order to expand in this class, we consider the finite shift where we just eliminate the first guy here. Now, then sigma of the string is this string. We have this lemma. If we take a subset of natural number which is invariant by the finite shift, then we have this condition, this expression, but we project it on the natural numbers. And we want to project it in the integers numbers. Then we give the notion of the P-adic dual. The P-adic dual of a number n is n minus p to the power n if our number is like this. The P-adic dual if is equal to n plus p to the power n if is in this way, and the P-adic dual of 0 equals to minus 1. Why this is important? Because the only way to appear an integer number as accumulation point of a set of a sequence of elements in E if it has the two types, 0, a great string of 0, of a great string of p minus 1. Then this is the P-adic dual, the P-adic dual set of E. And if you have that the E intersection n sigma invariant, and if the dual set is contained in E, then we have that E is projection of its closure. Then these are sufficient condition for this. And what about dimensions? So we recall here the definition of upper box counting dimension. Now we take where n. Here is the lower box dimension. N in this formula is the minimum of number of balls of radius p to the power minus n needed to cover F. Then we count this number and we divide by n log p and take the limit sub. This is the box dimension of F. With this, we have the result. If you take any set in ZP, then the counting dimension of its projection is bounded by the box counting dimension. However, we can find closed sets in ZP such that the counting dimension of its projection is strictly greater than the Hausdorff dimension of F. Then the notion of counting dimension, the Hausdorff dimension is more finer than the counting dimension. So this is the better, not so we can compare in any case the Bernardins with the P-adic measure. In some cases, we can compare the S counting measure with S Hausdorff measure. And the counting dimension we can compare with the box dimension in any case. Two applications. Fix a subclass of the power of Z. And we say that a subset of the integers numbers is S abundant in this class if there are a positive constant C and an increased sequence of elements in N such that the number of the elements of E and AK is bounded below by C, number of the elements of AK to the power S. We denote ARF the class of finite arithmetic progressions of common difference R. Then we have this nice application. Suppose that we have a set which is projection of its closure and is regular to the S-dimensional Hausdorff measure, which means this. If there is C such that this is bounded, then we have an increasing sequence of integers such that E is S-abundant on the class of the arithmetic progressions to the common difference P to the power nj. Then our set intersect several arithmetic progressions with common difference P to the power nj in this case. Here a necessary condition for we have a set in SP. If we take a set which is projection of its closure and it has bounded box dimension equals to S, then for every delta greater than 0 and n natural number large enough, there are at most kn bounded by P to the power n S plus delta arithmetic progressions of common difference P to the power n, say this sequence here, for instance, satisfying this inclusion, covering our set E, and our set E is in fact a countable intersection of this union of arithmetic progressions. So this is a necessary condition for a set B projection of its closure. Then all the preceding results can be stated if we take this a set E, subset of natural numbers, and the ideas behind these theorems is dynamical, and the integer Cantor sets, for instance, satisfies all the hypotheses in all theorems, B and D. Then interesting problems provide sufficient combinatorial conditions for this equality, provide sufficient combinatorial conditions for this equality, and for this inequality, and Banner's density of the set E is equal to 0. So if you want to see more, you can see Count and Hausdorff measure for integer and P-adic integers, is on archive, and this is it. Thank you.
Okay, very nice talk. Questions?